Hello, we continue with the second part on the tactical freight simulator. And in this part, we will deal with the more technical specification of all the models in the simulator. So, in an agent-based simulator of urban freight traffic, the population of freight agents is an important starting point. First of all, the logistical nodes, they are important logistical freight agents. This first illustration shows the three different types of logistical agents that we have in the model. First of all, in purple, we see the locations of all the multimodal transshipment terminals. In red, we see the locations of distribution centers for the handling of all kinds of commodity flows. And then finally, we also have indicated the locations of the depots of the different parcel carriers in the study area. Since these freight agents, they are very important for the generation of freight traffic, we use the known position of all these agents from public sources. Well, in addition to this, we also need the population for all the producers and consumers. For this, we have created a synthetic population. We have built a firm synthesizer that uses all the socio-economic data from the transport zones, and it discretizes the employment by different industry sectors into firms. This illustration shows detailed snapshots of the synthetic firm population in the city of Rotterdam. Now we know the locations of all the firms in the study area. We also need to determine where all the freight traffic or all the freight demand is allocated in the study area. This is done in the shipment module. So this module builds a set of all the shipments that are to be transported to, from, or within the study area. We do this by a stepwise simulation procedure. First of all the commodity flows are allocated to a distribution channel. Then vehicle and shipment size choice is being simulated, and the shipments are being allocated to the right consumer and the supplier of the goods. The result of this simulation procedure is a synthetic set of all the shipments in the study area. For model calibration, we use different data, such as the XML microdata that was discussed already, and data from the regional transport model. Now, let's discuss briefly those individual steps in the shipment module. The first step is the allocation to distribution channels. What this step does is to calculate the total volume of freight that goes direct or that goes indirectly either through transshipment terminals or distribution channels to consumers, or from a producer to these transshipment terminals or distribution centers. Well, what we did was quite a pragmatic approach in this. Since we have data on the observed market shares, we implemented the observed market share distributions of direct versus indirect transport and implemented this in the model. So the following figure shows for the different commodity types the shares of direct and indirect transport. And what we did is calculate the market shares for each of these flows and determine the total volume of direct and indirect transport. This is a rather straightforward approach based on observed statistics. So the next step in the shipment module is the vehicle and shipment size choice. So once we know the total volume of freight transported either directly or indirectly, we can determine the types of vehicles and the shipment size that is being used. We do this simultaneously. The reason why we do so is driven by the economic order quantity theory. This says that the logistical choice for the shipment size and vehicle type is determined both on the cost for transportation and the cost for inventory holding. You can imagine that if you transport your goods in larger volumes, this is more cost efficient. But if you also use larger volumes for transportation, you also need larger volumes for storage. So your inventory holding costs, they will go up. And so there's a trade-off between these two. We have implemented a model that takes into account the transport and inventory holding costs and applied a discrete choice model for this based on random utility theory. And we estimated a discrete multinomial logic model for this. This model was implemented in a simulation framework to determine the types of vehicles and also the shipment size choice. Now we've come to the last step in the shipment module. This is the selection of the receiver and the supplier of the goods, the consumers and the producers. So we have the discrete shipments and we determine who was the final consumer of this and from what producer did it come from. We do this by using Monte Carlo simulation and also using make-use statistics. In make-use statistics, it is described for each type of commodity which industry sector is the producer and the consumer of these goods. And we use this to calculate a probability for the synthetic populations in the study area to calculate for a shipment of a certain type of commodity, what is the probability for each firm to be the consumer of the goods based on the industry sector and also based on the size of the firm. This is represented in this probability function here. And the same on the producer side, of course. So if we want to know for a shipment in a specific commodity type, who was the most likely producer by calculating the probability on the make statistics and also the size of the firms. Well, this in the end gives a total set of shipments that have to be produced, have to be transported in the study area between the producers and consumers and the logistic nodes. Okay, after the shipment synthesis, we have the scheduling phase. And the scheduling module, what it does is to simulate all the daily logistic decisions, to simulate the formation of the round tours and also the time of the deliveries. For this, we have also implemented a stepwise simulation approach. There are two important decisions in this. First of all, it's the decision to add another shipment to the tour or to end the tour. And then secondly, the decision to select the shipment. We have calibrated a model on this based on the microdata that was discussed previously and also implemented a nearest neighbor search algorithm to determine the right order of the shipments. Output of this simulation procedure are tour schedules for the collection and distribution of shipments in the study area. This is similar to activity-based models that generate activity patterns for individuals. The scheduling module determines the vehicle patterns or vehicle schedules on a daily basis for freight deliveries. Now, if we go into the two different steps in this module in more detail, first of all, tour formation. And having a tour-based approach is crucial in having a better representation of urban freight traffic, because many of the urban freight transportation that takes place is part of a round tour. So what this model does was to simulate the formation of round tours. And what we did is to implement a simulation-based approach for this, opposite to very much optimization-driven vehicle routing types of approaches that are not able to simulate at this scale for such a big study area the formation of round tours. And we think simulation is a very effective way of doing this. Well, the approach, again, it's shipment-based, so it simulates at the level of individual shipments, is this shipment added to the tour or not? and also by applying discrete choice models. So the decision to add another shipment to the tour is based on all kinds of constraints, like the capacity of the vehicle or the duration of the tour, the distance of the tour, and the utility functions. It include transportation cost, commodity types, and vehicle types. And with this framework, we create a set of round tours with a set of shipments that have to be delivered. We also implement a small optimization algorithm to optimize the order of the different shipments that were allocated to one round tour. Well, the second part of scheduling is also to simulate the desired delivery time. For this, we have not implemented a discrete choice model, but what we did is we implemented Monte Carlo simulation, because we have an observed probability density function of all the tours in the XML data. So we know for each type of commodity at what time of the day the tours will take place. So what we did, we simulated a representative starting hour by using this probability density function and by using Monte Carlo simulation. This gives us the schedules and the exact times for all the tours in the study area, and also for the types of commodities. And as this density function shows, there is between the different types of commodities quite a good variation during the day. So it is important for representative round tours to have a good representation of different start time distribution depending on the commodity type. Now, in addition to the conventional commodity flows, in the tactical freight simulator, we have also implemented modules to simulate the delivery of parcels in the study area. So what these modules do, they simulate the demand and the last mile deliveries for all the parcels in the study area. This is very important because parcel demand is rapidly growing over the last years because of the emergence of e-commerce. And also many of the city logistic innovations, they are focusing on making the delivery of parcels more efficient. Think of the usage of parcel lockers or cargo bikes for the delivery of small parcels. So having microfreight available in your urban simulation model is very important, but not straightforward and not standardized. So therefore we have set up quite a straightforward way of simulation, also in a stepwise procedure. I will explain to you which steps we take for this. The first step is to calculate the parcel demand. The parcel demand, we calculated both for the business to business and the business to consumer segments. We know the total size of the business to business market in the Netherlands, and from this we know the average number of parcels that are to be delivered for each place of employment. The same goes for households. And by applying these rates to all the employment and population in the zones, we know the total number of parcels that have to be delivered. This is the first part. Second part, for each parcel we have to assume by which carrier it will be delivered, and also from which depot. From public statistics provided by the Authority of Consumer Markets, we know the market share of the main carriers in the Netherlands. There are 6 different ones, like PostNL is a big one, DPD, DHL, and using their market shares, we use Monte Carlo simulation to allocate each parcel to an individual carrier. If we know the carrier, we assume that the delivery of this parcel will take place from the nearest depot. We think this is a fair assumption because each carrier will optimize their operations to do the delivery of the nearest depot, of course. Once we know for each of the depots of the carriers, we can also start forming delivery tours in the same way as discussed earlier. Also the delivery of parcels is done in round tours. What we do in this is we have implemented a two-phased procedure. First, we build clusters of delivery zones using nearest neighbors search, and we form clusters of zones that have together a parcel demand that matches also with the capacity of the delivery vehicle. Once we know the individual zones, we also optimize the delivery order between those zones using a 2-opt algorithm. By doing this in this way, we also have a very efficient and effective procedure that is not too computational heavy. It's very efficient and gives representative patterns, like illustrated here on this illustration. Okay, the last technical module that I would like to discuss in detail is the network module. This module calculates the routes of each individual vehicle in the study area, and it calculates its emissions. This is important because emissions are used or required a lot for the impact assessment of different policies. The result of this study is a network with the intensities of all the vehicles on the network and also the emissions on each link. We have implemented a stepwise procedure. First step is the route choice. So for the vehicle, we know the origin and destination of the corresponding trip, and this trip can be part of the round tour. But for each of these legs, we calculate the optimal route, and we determine the optimal route using the congested traffic network from the available strategic traffic model for the study area. This way, we are taking into account the location of traffic congestion in the study area and the local accessibility on the network. So once we have determined also the routes of each vehicle, we can calculate on each of the link that the vehicle drives upon the emissions. Emissions are dependent on the type of link. It is known that the emissions in rural roads are lower than on urban roads per kilometer, and also on highways they are again higher. And what we did, we used road-specific emission factors, but also vehicle type-specific, and also take into consideration the load factor. We could make use of a European project called STREAM, performed by CA Delft, that provides these emission factors. By using these emission factors that are dependent on the type of vehicle, the load of the vehicle, and the type of road, we can have a very detailed calculation of the emissions. And even if vehicles are more heavily loaded, we can measure the impact. And also if vehicles drive more or less on highways, we can also measure the impact. The local outcomes of this can also be visualized in maps, as you can see here on the left-hand side.